Welcome everybody to an event organized by the American Nuclear Society's Risk-Informed Performance-Based Principles and Policy Committee. We call it RP3C. My name is Prasad Kadambi and I'm chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties we all have encountered with purely deterministic and prescriptive approaches and methods. We've been calling these approaches and methods RIPB for short. The Nuclear Energy Innovation and Modernization Act specifically mentions RIPB. If you look around, you will find it hard to find any place other than ANS, outside of NRC of course, that has as much information and guidance on RIPB. So I think ANS has played a leadership role in this, and we would like to offer its benefits to everybody in the community. Overall, there is a lot of guidance available on RIPB, but most people have not had reason to become familiar with the information. This is primarily because the conventional approaches still dominate most things we do, including standards development. RP3C has been having these community of practice events regarding RIPB and associated methods such as systems engineering to enable practitioners to share their knowledge and experience. We've been scheduling these sessions for the last Friday of each month. This month, we will have a presentation by Bob Youngblood in what I think of as a sort of triad. It began with a presentation in April by Stu Magruder of NRC staff. And he spoke about how the staff review is going to use performance-based approaches in order to deal with the wide variety of technologies and designs that the staff has to review. Then in May, I made a presentation about how this performance-based approach has been documented in NUREC BR 0303, which is a guidance document issued by the NRC. Today, we will hear more about the licensing aspects of using the performance-based approach, I think, by Bob Youngblood. And Bob, please take it away.
Okay, I'm off mute.
Yes, you are.
Oh, okay, good. Okay. Thank you. Good day to everybody. I have about 20 slides and I'm shooting for 40-ish minutes. And if I seem to have wandered off that path, and you can tell what slide number I'm on, please point out to me that I've strayed, and I'll try to pick it up. I was going to explain how this talk had been catalyzed by the Stu Magruder talk and Prasad's talk, and I actually have at least one slide from each talk in this set, and we'll get there. So the opinions expressed here are not necessarily those of INL, though of course they should be. But and then some of the slides were actually prepared years ago in work for NRC, and others were developed more recently during work for INL's Light Water Reactor Sustainability Program. So what the talk is really doing is bringing together ideas that have been around for a long time and kind of putting them all in the context of licensing a novel design, and mainly they're all the ideas I'll be talking about really all relate to margin. So, of course, then I have to begin with explaining a little bit about a probabilistic concept of margin. Everybody has a definition of margin, so I have to give mine. And what's illustrated there in the first bullet, I'll get to on a later slide, but it's a modeling point that says you should not throw away terms in your model that are comparable to the terms you're keeping. You want to make sense. And I'll actually point to a case where I think that's violated in ordinary PRA practice, kind of with a view to stressing the sort of thing you have to do right in order to apply the idea that I'm really talking about. I'll point to a slide from Stu Magruder's talk on 5043, which actually talks about how to go about applying for a prototype plant design. And the ANS Grand Challenge report from 2017 pointed to that same piece of the Code of Federal Regulations. And I just think it's an interesting thing. And that's really the fulcrum of the talk from an administrative point of view. Then I'll play a clip by from EBR2, from Pandoras Promise, actually, about EBR2, which EBR2 appears to have been kind of an example of the process we're talking about. It was not NRC licensed, but talk about what they called license by test was an outcome of the EBR2 lifetime example. And then, if you, having treated you to the YouTube clip, I'll get back to sort of dry definitions and what certain things mean, and then summarize. So, probabilistic concept of margin. I think a lot of people are familiar with this load capacity curve in the upper right there. And, some definitions of margin just sort of pick a point on the load curve and a point on the capacity curve and measure the difference and call that margin. And you've got actual failure point, or you've got, regulatory limit, or this or that. And in this talk, I'm really sort of stressing the risk-informed point of view. And then, so to do that, to do a risk-informed point of view, we really need to consider uncertainty and variability in both the load idea and in the capacity idea. And I'll be recapitulating a lot of this later, so I'll skip it. But this slide is showing in the lower left a plot of some reactor parameter trajectory as a function of time, and it was wandering along until some initiating event occurred, and then it began to go way high. And that could be a temperature or a pressure, but it's some sort of excursion. And the idea that we need probabilistic margin for is that if there's variability in how high it gets, and if there's variability in the actual failure point, and there's some chance that the actual parameter will exceed the failure point, then that's an issue. And so when we say margin, what we need to mean by that term is that that the gap we're talking about so exceeds the probability of exceeding the failure point that's what margin really ought to mean. And there are actually, in a way, two kinds of margin displayed on here. One is the value reached by the parameter, and the other is the rate at which the parameter started to take off as a function of time. If you don't have time to react, then you lack temporal margin, and we really sort of want both. But it's and I think Prasad had some version of this slide in his presentation, and that's what I think prompted him to suggest that I give this talk, because this slide is decades old in NRC work. Anyway, Now, when you model these things, I'll get to an example of this shortly, but people model success paths when you do safety analysis report. Well, I'll illustrate the inequality on the next slide. This is showing an event tree. The top path there is the safety analysis report path for some particular incident. And if it's a design basis event and you've got the equipment you need to respond to it, and some subset of that equipment works properly, then you're okay. But in another path, and I have in mind here feed and bleed for pressurized water reactors, that's not really analyzed in the safety analysis report necessarily, or it certainly wasn't a generation ago. So while people have done backflips to achieve enormous margin in the design basis response to the design basis challenge, much less was done to establish the viability of feed and bleed. And so I think apparently it will work most of the time, but from a methodology point of view, the margin is very different. And in some cases, depending on the PRA you're talking about, the margin is actually violated. So that was illustrated in the EPRI report cited here. The number is given down there. Those guys analyzed margin in PWR feed and bleed, identified a bunch of variables listed in the sub-bullet of the first main bullet. A bunch of different cases there that actually span a couple of ordinary PRA success paths, and found that some of the success paths people would normally invoke actually fail some of the time as a result of this sort of thing happening. If you're counting on a safety injection pump that isn't super high head, and the PORV throat capacity is a little less than you thought, or maybe you're actuating it a little late or something like that, you may not actually feed enough to achieve the requirement. So what they found in this report was that if you started charging pumps, which really are high head, then within the space of samples that they did, the charging pumps always worked, but the high pressure injection pumps didn't, but PRAs would typically credit them. So to me, that's just an interesting example of how margin needs to be thought about beyond the design basis. And with all that as background, now to Stu Magruder's talk. I highlighted the part below that's, I think I copied this slide pretty much out of his talk, except I highlighted the part that interested me. They'll consider, I'm paraphrasing now, but you can read it. They'll consider a novel design if, and at item 1 there really means if you really know a lot about that design and you can show it, tests, analyses, and so forth. Or item 2, there's been acceptable testing of a prototype plant. And of course, to build that prototype plant, you're going to have to address additional requirements on siting, safety features, or operational conditions. And I put the word margin at the bottom because that's what we really mean by the title of this talk, Licensing Advanced Designs, is really that they may let you build a prototype if you put in margin, and that's part of the EBR2 story. Now, not to say that EBR2 was NRC licensed, but they built it with a lot of margin, and we'll get there. So, in the ANS Nuclear Grand Challenges report, actually, came out in 2017. Andy Klein wanted to do that, and it's actually it captures a lot of thinking about what ought to be done to really help. And one of them, expedite licensing, actually contains this excerpt shown below. Institutional difficulties could be avoided by first constructing and operating a prototype plant that has sufficient margin, and so forth. And it goes on to cite 10 CFR 5043E2, which is the piece I showed you a minute ago. So this grand challenge is saying, hey, you know, look at that. And now, that said, I'm going to take a risk here and try to play a YouTube clip. This is from the movie Pandoras Promise, a CNN movie that came on a couple of years ago, and it's mostly about showing environmentalists who used to be anti-nuclear becoming pro-nuclear in order to do climate change.
It was called the IFR, the Integral Fast Reactor. The budget was about $100 million a year.
Can you all hear that?
1,500 people, scientists, engineers, supporting staff.
Yes.
This was a very big development program. But you've got to test it.
I'm going to pause him right there. When I came to the lab in 2008, people were talking about science-based licensing, by which they meant that simulation is so good now that we can just believe it, and we can get away without building these expensive facilities. And I like to look at the expression on Charles Till's face here, and the thought I think he's trying to beam into your brain is to just say no to that stuff. You really need to test.
Calculations don't.
We can hear the video, but we can't see it.
Sorry?
We can hear the video, but we cannot see it. You need to share the browser window.
Oh. Thank you.
No problem.
Yes, it's my fault. I shared an application instead of my screen. Let's see, stop share. And now share this one. Do you see it now?
All good.
Yeah. Yes.
Okay. Okay, so this guy is Charles Till, and you just heard him say that you've got to test. And that's the story that this thing is going to tell now.
Facilities that say, if we have an accident of this kind, what will happen? We did 2 experiments to demonstrate some unique safety features that reactor has that others don't have. And invited people from all over the world to come and witness it.
Minus 2 minutes. Station blackout is a term that's used by NRC, the safety folks, to describe the situation where one loses all AC power. You assume that you lose off-site power. You assume that you're getting no AC power from your own turbo generator. You assume that your first diesel started up and it failed to start up. The second one started to start up and it also failed. So you end up dead in the water with no AC power.
This experiment was almost a direct parallel to what happened at Fukushima. It was eerily similar. We ran a reactor at full power, disabled the shutdown system, so the operator had no ability to shut the reactor down. And we shut off the cooling system, didn't extract the heat, so we just let things get hotter. In most reactors, you can't do it. No reactor I know of that survived that accident. We have a meltdown. The international audience were watching the temperature going up like that, straight up. They turned around like so to see if I was or if the Argon guys are running. By the time they looked up again, the trace had turned like so, and it was on its way down, and the reactor just quietly shut itself down. No action required of the operators, no action required of the safety systems, nothing. You could just stand back like this, watch the dials if you wished, and the reactor shut itself down.
30 seconds for test time.
Well, in the afternoon, we started.
So now I have to go back and reshare my slides, I think. Are you seeing them?
Yes.
Okay, thank you.
Yeah, we see a slide now. Bob.
Okay. So now, so EBR2 was built as a test reactor, and they did a lot of work over a period of years. When the guy narrating the main thing there, Charles Till, he sort of came in the early '80s with the idea of making kind of a soup to nuts, you know, burn your fuel, recycle your fuel, burn the new fuel, and so forth. That's why it was called the integral fast reactor system. But the reactor they were running was EBR2, and they had done enough work on it to know that that experiment they did was really, you know, perfectly safe because of reactor feedback. So they're talking about, you know, I don't know if the narrative was clearly audible, but they shut off all AC power to it, having disabled the scram system. And so, you know, most plants that would be a bad idea, but they got away with it, and they knew they could get away with it, and that's margin. That's margin with knobs on. And so another guy who doesn't show up on screen there, John Sackett, he used to call this license by test. And so what he meant was, you know, build your over-designed prototype, run it, learn about it, and, you know, then your licensing path is going to be a lot clearer than it is if you are sort of doing analysis and hand waving and limited separate effects tests. I actually spent time trying to figure out the origin of that phrase, license by test. And I think it was just in the air in the mid '80s when those experiments were done. The other thing, to go back to the top there earlier where it says key safety features were passive, John actually believed that this had an influence on the design of the passive plants. The EPRI utility requirements documents on passives came out not too long after these experiments were done. And I actually called some people up asking them about, you know, whether the EBR2 experience had influenced them. And they said, no, actually. It's just was just in the air, in the atmosphere of the 1980s. But so there's a case where they over-designed, they instrumented it up to a point, they ran it, they learned a lot, and so to me that's apart from having not gone through NRC licensing, that's kind of close to the 5043 thought process. So. You know, at some point, for a different audience, you know, for a popular audience, I would just stop there and summarize. But I think for this, I'm going to put you through a little bit of terminology here: allocation and implementation. And this is now, suppose you were going to think about actually making a safety case for a prototype plant. let's just scratch the surface of some of the thoughts that would need to go into that. This slide actually dates back to work I was doing for Prasad probably in the late 90s. And there was I don't even remember whether it was NEI or Newmark, but one of those entities wrote a report that, and this figure in that report actually clarified things for me. We need to do two things in formulating a regulatory approach. We need to decide what's important, what are we counting on in our safety case. So, like, for example, what's going to be safety class? And, what do we need to take credit for in order to meet regulatory requirements or business requirements or whatever requirements we need to report? What do we need to rely on? That's the stuff on the left, and that's approximately where risk informing sits. So risk informing might mean, write down everything on the left that makes any sense at all. And then how do we know that it's coming true? How do we make it come true? Because we've said things like on the left, like we need reliability of so-and-so and availability of so-and-so and actual physical performance of so-and-so. How do we know we're getting that? Okay, we're going to hand in an analysis that says we're going to get that, but how do we know we're getting it? And classically, of course, the one way to do that is by imposing things like in-service testing requirements or in-service inspection requirements and a lot of stuff. And of course, performance-based approaches are part of that. So those two questions are partly formulating a regulatory alternative, but they feed back into design as well, because if you need to rely on a component in such a way that it's got to be a 10 to the minus 9 failure probability, you're never going to be able to show on the right that you make that come true. So you need to make a different design choice. So all the things you might do to convince yourself and the regulator that you're getting the performance you might need, those are options on the right. And you can imagine options that are a blend of a pure thing from the left and a pure thing from the right. And I think in reality, any intelligent approach is going to take combinations of things on the left and combinations of things on the right to get there. This, by the way, I used to wonder when I entered the field, I used to wonder why regulators weren't worried about common cause failure, because I couldn't see it in any of the regulatory requirements. And all the systems that they were licensing, well, many of the systems they were licensing were not particularly diverse. They would have they would have identical divisions, redundant identical divisions. And even when I joined the field, risk people were well aware of common cause failure, and it just seemed to, that practice seemed to fly in the face of what people had learned about common cause. And it turns out that back in the day, I learned this from Roger Mattson, who was pretty high up in NRC in the 70s and early 80s. He says back in the day, people thought that the requirements they were levying would prevent common cause. And it's hard to find where that's written down, but it is out there. After Fukushima, there was this ASME report on a new regulatory construct, and that report actually says that. But anyway, allocation, deciding what SSCs, operator actions we wish to rely on, deciding what level of performance we need from them, deciding how much credit to take. Is in one application, it's deciding how much credit to take, recognizing that taking credit costs money. And of course, the answer to that question classically is basically where you decide where your special treatment is going to come from. But in PRA, as you probably all know, a lot of stuff that's not safety class needs to be credited if you're going to get answers that people want to live with. So classically, people use the design basis approach, choose design basis accidents, require single failure proof mitigation capability, and so forth. And the next bullet down, use of a risk model. Earlier, the slide I showed the event tree with different paths on it. I think a modern approach for a Gen 2 type plant would take credit for multiple success paths, and that would be the point. The complement of success paths that collectively satisfy your performance target. You know, if that makes technical sense to you and gives you the risk number NRC wants to see, good. Now, I think advanced designs may not have many success paths. They may be banking so heavily on passive performance that that it's just one really good path, and I think that poses an interesting challenge to thinking about it. Implementation, of course, the old approach is to prescriptively gold plate what was safety class. Performance-based, and there are really, I wasn't going to go into this, but there are really a couple of dimensions to performance-based. The one I'm personally anchored to has to do with verifying on an ongoing basis that your plant's systems are working the way you said they were going to work and the way you need for them to work. So measure performance to confirm needed level of performance is being maintained on an ongoing basis. So things like containment leak rate testing are an example of that, but so is just starting pumps once in a while to make sure they still work, and that sort of thing. And then, of course, well, we don't need to get into process-oriented, but that's just there to illustrate that there are a lot of different ways to make sure that what you're claiming is coming true. Performance-based. It's a very old term, and I think the meaning of it is morphing a little bit. I think it's really more general nowadays than the previous slide reflected. It's a shorthand term for an approach to implementation that's less prescriptive, more goal-oriented, and more efficient. How do we know it's more efficient? Well, because if it were less efficient in the sense of costing less for licensees to implement, but still having the same meaning, if it were less significant, people would just revert to the old ways of doing things. You know, they're an option, but in principle, if you can show that something actually works in some novel way, as long as it's convincing, you know, that's very likely to be better than what somebody would have dreamed up in trying to design a prescriptive generic regulatory requirement. So, margin in allocation and implementation. There's, how would we operationalize the 50-43 thing that I pointed to earlier? What do we have to do? What's the beginning of what we have to do in order to actually apply that idea? And I've already stressed you would allocate margin in the design, a lot of margin. EBR2 was way over designed from the point of view of physical margin and temporal margin. I mean, they weren't, of course, certain that it was over designed until they'd run it for a while, and then they knew it was over designed. But then point B, under implementation, in order to do what you want that prototype to do, which is help you make your case, you want to instrument that plant very thoroughly in order to provide a means of measuring margin all the time. And you know, EBR2, actually one sense in which it was over-designed is that as sensors failed in the high radiation environment of the core, they had enough redundancy in the sensors and enough margin in the plant that they knew they didn't have to worry about it. So, you know, that was a sort of a two-pronged occurrence. But in the prototype, of course, in the prototype application, if you were consciously setting out to do 5043, you'd want lots of sensors for lots of reasons, because you want to really nail plant performance so that you can argue, so that you can optimize the design that you want to build 100 of. You know, you don't want to build 100 over-designed plants. You want to build one over-designed plant and then optimize your design and then build 100 of the optimal version. So licensing novel designs on the basis of margin. I think it's obvious even to me that I haven't answered all of the questions that you would need to answer. I've just tried to bring together a couple of key concepts, sort of alluding to the Stu Magruder talk and one of Prasad's talks. The general idea is to propose a prototype facility that's over-designed in ways that are necessary to compensate for a current lack of testing. So rather than build a facility whose purpose is only to make a measurement, you're building a prototype that will actually work, maybe actually make power, but will support a program of testing and data collection so that you can optimize your subsequent design. To do that, in my parlance, you'll need to identify a set of success paths that are going to make your safety case. They collectively satisfy the top level performance requirements, but more than that, they have abundant margin, because, as Charles Till would stress, maybe we can't absolutely trust simulation the way people in the late 2000s, well, not the early 2000s, before 2010, what people were arguing, that we can, you know, the simulation will be so good we won't need test facilities anymore. And then, of course, figure out how to assure on an ongoing basis, you know, in operation, that those paths actually have the margin that they need to have. So that's what I meant to cover, and thank you for your attention.
Thank you, Bob.
Thank you, Bob. Was that the last of your slides, Bob?
I have some backup slides, but I'll only use them if the questions make me.
Oh, okay. Well, I guess, you know, while I wait for people to generate questions, I just want to point out that, you know, one of the key aspects of what you spoke about was this idea of physical and temporal margins. And that's something that came out of, you know, the late 1990s, the work that the commission did, and, you know, the white paper on risk-informed performance-based regulation, and the formal definition of a performance-based approach, which called for, you know, making sure that you have the right parameters, that you have criteria associated with the parameters, that you have flexibility, and you know, and also that the criteria should be set in such a way that even if you violate the criterion, you do not get an immediate safety concern. So all these things came together in the guidance document that you and I worked on, Bob. That's NUREG BR 0303. And as far as I know, it's the only place where temporal margin has been defined in sort of a formal way. You know, so when you showed those curves with the physical margin, you know, it's not clear that when you have just capacity and load, you know, how to take care of any time variability or a dynamic situation. But anyway, the point is that, you know, I'm not aware of any place where temporal margin has come up. And, you know, I'd like to ask you, Bob, do you know if there is any other place where temporal margin shows up as, you know, a defined term?
Well, I think in procedures, in analysis of procedures, you know, the HRA people are always worried about the time frame available, but I think you're speaking of a different, you're speaking of setting up the design and the procedures in the first place so that people are given sufficient time to react. And you've also sort of tied it to item 4 in the NRC definition of performance-based, which was the business about not tripping a criterion. Back in the day, I always thought that just had to do with fixing the criterion. In fact, the case of it that I remember was people were trying to invent a performance-based regime for shutdown operations. And of course, in shutdown operations, you want to avoid, if you've got the head off and people are in containment and so forth, you want to maintain decay heat removal in such a way that you know, the core is not threatened under those conditions. And somebody proposed setting a temperature criterion such that if the temperature criterion were tripped, you'd have to, you know, then you'd know that you had done something. And the problem with that was that some of the causes for a high temperature excursion wouldn't be too threatening, but some of them would. And so if you get a high temperature because you've lost shutdown cooling, that's fairly scary, and that's not so you don't want to peg your regulatory oversight function to having lost all of shutdown cooling. And so that, to me, that was a case of the commission's 4th element there, where tripping a criterion should not in and of itself be a threatening circumstance. So, you know, all that said, you know, I have to give you credit for reminding me to at least mention temporal margin somewhere in the slides. And I would say, actually, the slide that I have for that wasn't a super example of it, because what this slide has on it you can see the plot bending over and coming back down, and of course in the real event you don't know what's going to happen next. So you'd rather see things change slowly, despite, you know, in the EBR2 example, the temperature just shot up, but they already knew it was going to come back down, and that's why they didn't worry. But it's, you know, in retrospect, if I were making this slide again, I might make it patterned after the graph in the YouTube clip that I showed. By the way, that movie is a good read. You know, I'm not getting a kickback or anything, but the movie is a I mean, it's a good watch, shall we say. You can stream it.
Okay, you know, I'd like to ask if anybody in the audience has questions. You're welcome. You don't need to use the chat function at this point if you want to just speak up.
Yeah, Bob,
Yes?
this is Mike Mulheim. I have a question. You talk about identifying the success has that, do they do that using the current PRA approach, or do they use a different and specifically go to identify success criteria?
Well, being who I am, I always think in terms by. To me, I'm always implicitly thinking about an event tree success path, and you know if you have a comprehensive logic model of your plant, or you know maybe we need to be talking about post logic modeling these days, but to get the idea across, all the ways you have of succeeding are success paths, and some of those ways might not have enough margin to be defensible in all contexts. So to me, it's an interesting analysis and an investment decision to decide what you're going to hang your hat on. And so I'm showing on this slide a bunch of okay paths that maybe you don't need credit for all of them, and maybe some of them are going to be hard to ensure on an ongoing basis, but the investment decision is to choose a collection of okay paths and hang your hat on it, assuming that you have analyzed a reasonably comprehensive set of initiating events, and assuming that your success criteria are actually validated the way people may do now, but certainly we're not doing in the early 80s, which is where this counterexample came from. You know, the EPRI guys, not EPRI guys, it's an EPRI report. They were Jensen Hughes guys. Or no, I guess at the time they were Aaron guys working for EPRI, analyzed paths and just showed that some of the paths people take credit for don't always work. So you shouldn't choose them. You should redraw your event trees that where the okays really are okay, and quantify that way.
Any other questions?
I could call on people. I just got out of a meeting a little while ago where the moderator was actually calling on people, demanding that they ask questions.
Well, I'd like to ask Bill Reckley if he has any questions, now that you mention it, you know.
Do you want a sloppy Joe or a stir fry?
He's come off mute.
I didn't have any questions per se, Prasad. I will say that as we're working on trying to develop new processes that take more credit for PRA, the question of margins and how we use them in regulatory processes is coming up, and we're trying to develop those now. For example, if the licensing basis becomes more PRA based, even today, what I was working on is how do you consider margins within the PRA in terms of maybe specific events like being modeled here, but then also in terms of cumulative measures as the parallel for something like 5059 to evaluate plant changes. So it's a very timely discussion, and good job, Bob. I was just listening in for ideas, to be honest.
Well, thank you. Something in the middle of your comment, I think I meant to explicate this inequality maybe more than I did. You know, in WASH 1400 of all places, at the time of WASH 1400, people still had residual concerns that in a true large break scenario, low pressure injection might come on, but the core might still sort of fail to be cooled. And they actually did a sensitivity study where they added a basic event corresponding to left side of this inequality. You know, like the equipment worked, but the core still wasn't cooled. To see how much difference that basic event made, I think they put in a 0.1 or something, and I'm not sure I approve of what they did with the result. You know, the result was that the overall bottom line didn't change very much, because from large loco they weren't getting that big a contribution anyway. But it's the I think that in the early 80s, certainly in the 70s and in the early 80s, there was a systematic neglect of this kind of issue where the logic would say that the system did what you told your model it needed to do, but for variability reasons, maybe initial conditions or whatever, the function still wasn't satisfied. And so I think that this inequality is kind of a neglected thing that belongs in some of the standards, and I haven't found one that contains it yet. But to a modeler, it's an obvious thought. If you're throwing away high order negligible terms, they ought to be negligible. And once you've specified your mission success criteria, why, they need to be satisfied at a high level of probability.
Bob, since we are running short on time, there is a question in the chat that says, how would defense in depth fit into your discussion on licensing by margin?
Well, I think, one reason that the licensing modernization project really caught my eye is that I believe its discussion of defense in depth is just highly regarded by people. And so if I trusted myself to quickly pull up the defense in depth figure from the LMP, I would start speaking to its bullet points. I think EBR2 had a confinement, but not a containment. And they had arguments why confinement was okay, but they had one. They didn't try to get away without one. So I believe, I don't want to waste everybody's time sort of babbling, but I believe that defense in depth is certainly addressable within a framework like this. And I think even in the slides that I have, I think somewhere part of margin in a probabilistic sense is having enough backups to be really sure in a probability sense that you're not going to exceed your performance criteria. So I'm reasonably confident that the answer is out there, but I probably won't nail it in the minutes that we have.
Okay, since I don't see any more questions, Bob, I want to thank you for the presentation. I think this is the sort of open discussion that I've always hoped these community of practice sessions will lead to. I invite others who are on this call to think about what other community of practice talks might be possible. And if you yourself would like to offer a presentation, please let us know. But in the meantime, I think, again, I want to thank everybody for tuning in. I hope you found it fruitful for the time that you spent with us.